We tried everything to make our Raspberry Pi 5 the world's fastest Raspberry Pi 5. And that involved updating the operating system, swapping out the crystal oscillator, using liquid nitrogen, and beefing up the power supply. In this video, I try to share my findings and my experience while trying to squeeze the most out of the Raspberry Pi 5 using some ElmorLabs tools. I hope you enjoyed the video.
Let's start where we left off. In Scatterventure number 77, I overclocked the Raspberry Pi 5 to 3 GHz with a slightly improved air cooler. In preparation for the record attempt, it's important to prepare the operating system first. Coming from Ubuntu in my Scatterventure guide, there's two things we can improve. First, change to the official Raspberry Pi operating system, and second, apply the NUMA patch. The official Raspberry Pi operating system can be easily downloaded from the website. Alternatively, you can also use the Raspberry Pi Imager software, which does all the hard work for you. I first learned about the NUMA patch when discussing Raspberry Pi overclocking on Tom's Hardware Guide's The PiCast a couple of months ago. I followed Jeff Geerling's guide on enabling the NUMA patch. Combining the Raspberry Pi operating system and applying the NUMA emulation patch improved the benchmark performance significantly.
The next step in preparing the Raspberry Pi 5 for higher voltages and frequencies is, of course, improving the cooling. And preferably, we want to use subambient cooling or extreme cooling like liquid nitrogen. The place to be for liquid nitrogen testing in Taipei, Taiwan is, of course, the ElmorLabs office.
The Raspberry Pi 5 has a small footprint PCB with quite a lot of tall components spread around the PCB, so we can't use a regular container like our AI LN2 container or the ElmorLabs Volcano. However, we found this tiny chipset LN2 pot. This container is heavy enough that it can just sit on top of the SoC and provide enough cooling even at ambient. After all, the SoC is barely using any power. I first ran Geekbench at 3.2 GHz as a performance sanity check, and I achieved 1000 in single core and 2000 in multi-core for the very first time. Then I tried increasing the operating frequency with low ambient temperatures of 20 degrees Celsius. However, as you can see, with ambient temperatures, I could only set the clock to 3.6 GHz. Once I tried 3.7 GHz, the Pi would lock up. Reducing the temperature to minus 40 degrees resulted in the same type of crash. The Pi just locks up at 3.7 GHz. Strange. I also hooked up the ElmorLabs EVC2 to talk to the Renesas PMIC directly and elevate every voltage rail. However, none of them seem to have any impact on the maximum clock frequency. For those interested, the Raspberry Pi 5 only starts having operating problems around minus 90 degrees Celsius. Not bad at all.
The lack of temperature scaling is a little bit concerning because every modern SoC should scale with temperature and voltage. So the fact that we're not seeing any scaling with temperature implies that maybe we're also not going to see any scaling with voltage. But there's only one way to find out. In the Scatterventure guide, I mentioned that the Raspberry Pi 5 shuts down when we use really heavy workloads that rely on the neon instructions. If we have a closer look at the passmark benchmark, we find that the benchmark crashes specifically at the neon subtest. Furthermore, we find that it crashes also at lower frequencies even though it passes 2.9 GHz without the firmware voltage workaround. If we track the current voltage and power of the VDD core during the workload, we find that the neon subtest is significantly more power intensive than any other subtest. To address this problem, as well as surpass the 1.2 volt voltage limit, we beef up the power circuitry. And again, ElmorLabs comes to the rescue with their Ample-X1 power card.
The Ample-X1 is a power card that uses a single-phase step-down buck converter. It is optimized for operating from a 12-volt power supply, and the parameters can be easily monitored and controlled digitally by connecting it to an ElmorLabs EVC2.
To hook up the Ample-X1 to the Raspberry Pi 5, we need to do some definitely warranty voiding modifications to the Raspberry Pi 5 PCB.
We have to remove the inductors of the 4-phase SoC to disconnect the PMIC from the SoC. We also have to scratch off the PCB mask to expose more of the copper plane for VCC and ground. We have to solder thick, short wires between the Raspberry Pi and the Ample-X1.
Once that's done, we have to check if the Raspberry Pi 5 still boots up. And that's no guarantee because sometimes the SoC has a two-way communication mechanism with the PMIC to ensure the correct boot up procedures are followed.
Luckily, it still works. The important step is to turn on the Ample-X1 power to the SoC before connecting the USB Type-C to power the other rails and initiate boot up. Now we can use the EVC2 software to adjust the output voltage as well as monitor output current and power. You can use the EVC2 on a secondary system like a Windows laptop or use the unofficial Linux package that I'm showing on the screen here. Here's an example of the Ample-X1 peaking at 23 watts during a passmark run.
With the beefed up power circuitry, we can now try voltages above 1.2 volt. We tried up to 1.55 volt, but again, no frequency scaling. We kind of already suspected that this was the case because there's also no scaling with temperature. But why is there no scaling? There are many reasons why a modern SoC wouldn't scale with temperature or voltage. It could be some PLL locking issue like we saw on Intel Tiger Lake, or there could be parts of the ARM SoC that also get overclocked that we can't control directly. Most of these ways that the SoC wouldn't scale are very hard to debug without the proper development tools. However, there's one thing that we can check, and that's if the PLL has some problem. And how do we do that? By swapping out the crystal oscillator.
The idea is simple. We swap the fixed crystal oscillator with a variable oscillator. That allows us to change the PLL ratio for frequencies exceeding 3.6 GHz. The default clock crystal is a 54 MHz crystal, which is on the backside of the PCB. It can be removed with some heat.
Ooh, look at that.
Next, we replace it with the ElmorLabs external clock board. Now we can adjust the input clock lower or higher than the default 54 MHz. Upwards, we immediately run into a limitation of about 56 MHz. However, downwards adjustment was much easier, and the Raspberry Pi 5 could go as low as 46 MHz. With 46 MHz, we can set the ARM frequency to 4000 MHz. And as you can see, the Broadcom VCGen command tool also reports it as 4 GHz. But of course, the real frequency is much lower because the crystal oscillator reference clock is lower. The actual frequency is 4000 divided by 54 multiplied by 46, so about 3.4 GHz. Again, we run into the same frequency wall as we saw with the temperature and voltage adjustments, about 3.4 GHz for benchmarks and 3.6 GHz as maximum configurable frequency. Oh, and I did try to run Geekbench at the fake 4 GHz, and good news, it was able to catch the result isn't legitimate. Great job.
So that's it. We tried everything to get our Raspberry Pi 5 to run at 4 GHz, including using liquid nitrogen, beefing up the power circuitry, and even swapping out the crystal oscillator. But we can only see 3.6 GHz, and we achieved that with regular ambient cooling. So that's a little bit disappointing, but that's not to say that this wasn't an interesting project. I learned a lot about Linux, and I got to do some really hardcore hardware modifications. So I still see this project as a bit of a success. It was still interesting to learn all of these things. Anyway, I thank you for watching and the patrons for the support, and see you next time.